Hello everyone, we are solving question number 53 of GATE 2016 Chemical Engineering paper, and the question is, for a step input, the response of second order system is given by the given equation, where Kp is the steady state gain, zeta the damping coefficient, tau is the initial period of oscillation, and phi is the phase lag. The overshoot of the system is exponential of minus of pi zeta upon under root of 1 minus zeta square. For a unit step input, the response of the system from an initial steady state condition at t equal to 0 is shown in the figure. What is the natural period of oscillation of the system in seconds? Let's take a look on the solution of this question. So let's just first interpret this graph. In this graph, we have been given the response of the second order system, and we can see that around 1200 seconds, the value reaches a steady state value of 350. So we can write this ys as 350. The other thing to note is the time period of oscillation. Period of oscillation. So that is the time taken by the system to reach to successive higher peaks or lower peaks. So basically, time taken by the system to achieve either this or this. So both of that will be same. So this entire time duration is 200 seconds, which is divided into 4 interval. So it will be basically 50, 50, 50, 50. So from this plot, the time period of oscillation, we can write it as, let's just call it as t is equal to, so it will become 200 by 2, that is 100 seconds. The other thing we can calculate is this. We can see that the maximum value over here is 430. The minimum value over here we can see it as 250. So we can call this as A and this as B. So we know that the ratio of A upon B is known as overshoot. So overshoot, let's just call it as OS will be A upon B. So here A is 430 minus of 350 upon 350 minus of 250. So this will become 80 upon 100. That is overshoot, we will be getting it as 0.8. And in the given question, we have to find the natural period of oscillation in seconds. So that is tau. So we can get this natural period of oscillation by using the formula for this period of oscillation. So if we write this period of oscillation formula, then it will become t is equal to 2 pi tau upon under root of 1 minus of zeta square. Over here, this is natural period of oscillation. So once we get this damping factor zeta, we can use this period of oscillation formula to get the desired value of natural period of oscillation. So let's take a look in the further solution. So what we have calculated until now is, we have this overshoot is 0.8, and the formula of overshoot we have been provided in the question. It is minus of pi zeta upon under root of 1 minus zeta square. Minus of pi zeta upon under root of 1 minus zeta square. So we need to solve this equation to find the value of zeta. So we will take a natural log on both the sides. So we will be having ln of 0.8 is equal to minus of pi zeta upon under root of 1 minus zeta square. So in this we can write it as zeta upon under root of 1 minus zeta square. So 0.8 2231 upon 3.1417. We can solve this and we will get it as 0.071. We can take the square on both the sides and it will become zeta square upon 1 minus zeta square is equal to 5.04 into 10 raised to minus 3. Again we can take the inverse. It will become 198.13. So that is 1 upon zeta square. You can write it as 199.13. And from this we can find the value of damping factor or zeta as 0.07. So now we have this value of damping factor, that is zeta, so that we can put it in the formula of this time period of oscillation to find this natural period of oscillation. So T is 2 pi tau upon under root of 1 minus zeta square. The time period of oscillations from the graph we found out to be this time period, that is 100 second. We can write this as 100 is equal to 6.28 into tau we have to find upon under root of 1 minus 0.07. So from here we can write this tau as 100 into, this will become 0.997 upon 6.28. So we can calculate the value of this tau as 15.87. So the units was in minutes. So the final value of the natural period of oscillation tau will also in minute, that is 15.87. So from the given options, we can select the natural period of oscillations as 15.9.